Thanks, Pankaj, and I thank the organizer for inviting me to this conference. Okay, so I'll start from recalling the result of Heath-Brown. So I will confine to only the 4 variable case. So this be a quadratic form. Over Z. And the problem we are interested in is count solutions in integers. To f of okay, so now if the form f is a definite form, then I don't need to say anything more because, for example, suppose it's positive definite. So example, maybe I'll split the board into some parts. So you can ask, equal to n equal to what? So we want a main term and an error term and asymptotic formula. So this makes sense because the form is definite, but if the form is not definite, if it is indefinite, then I need to specify the size of the variable xi. So in general, the question will take this form that, so let's say w xi, or maybe, okay, where is the, okay, before putting the smooth weight, let's put 1 and let's say m is integer, is inside some set that grows, size 8 power 4 equal to, where bx is an expanding region going to infinity. So for example, you can take equal to say minus x to x to the power 4. Or you can take a ball, an L2 ball. This is an infinity ball. Okay, so let's recall what Heath-Brown proved. This is from 96, I think, Taylor's journal. This is that paper that I think Binay explained. So, yeah, so the thing is, there are two, so he considers two cases. N is 0 and n is non-zero. When n is non-zero, he takes the variable to have size square root of n. So then what happens is, let's say f of m equal to n, and then w of m by p. So this will have a main term of size n. So let me write Cn plus O of n power 3/4 plus epsilon. This is for n non-zero. And 2 f of m equal to 0 w m by p. Oh, I should say that here I take p equal to square root n. And this sum, this becomes the main term of size p square, but there may be some log p also, but let's say, let me write cp square. And the error term is of size p to the 3 by 2 plus epsilon. So in this case, this was improved by Getz. So in case 2, Getz improved the error term to O of p to the 1 plus epsilon. So notice that both are p to the 3 by 2 here. In the homogeneous case, you can improve the error term. I will explain how it was improved. So let's recall what happens, how you prove it. Oh, I should make one more remark. Okay, let's get it over with. So in the definite case, we are in a happy situation because we can remove the weight. Can choose the weight so that we get an exact count. Meaning, we can have a situation like this. And that is explained at the very end of his Brown's paper, that you can take a weight of this form. It is 2 times, if I remember correctly, f of I think it is fx minus 1, something like that. And so it is, the support is, so here W will always be, it will be made out of forms like this, functions like this. So this is 0, minus 1 to 1. So the weight will depend on the form, and then you will see that that it becomes exactly 1, and you don't lose anything. But in other cases, if you count with weight, that's quite different from putting a 1. Okay, that is one thing. So this is a remark. And in the definite case, something even better happens, because I should not cross that. Let's go. So remark 2. So in the definite case, a better way is to view the representation number so representation number means you count f of m to n as coefficient of a theta series, right? So these will be theta series, and then every modular form you can decompose as Eisenstein series and cusp form, and at the level of coefficient, that will give you precisely the main term and error term. So let's say f, and write f as some e plus, let's say, f naught. So this is the Eisenstein part. This is the cuspidal part. Maybe just write cusp form. And then, so what happens is, so let's call it RFN. So RFN will be some, some coefficient of the Eisenstein series. So let's say it will be some Cn, and this is the coefficient of the cusp form, and then by the Linz bound we have a good bounds. We have O of square root n. So you can improve all these bounds. So that, in fact, it is remarked in Heath-Brown's paper. Okay, so that was some remarks that in the definite case we are in a very good situation. But I will be concerned mostly with indefinite case. So let's recall how it is proved. So Heath-Brown's method. So he uses expansion of the delta symbol. In the style of, DFI style expansion of DFI type. So that roughly says that delta n equal to CQ by Q square sum over Q E A mod Q star E NA by Q H small q by capital Q n by capital Q square. And so So what you want is this count, W m by P, Fm equal to 0. So you write it as P into delta of Fm. So I'm only considering the homogeneous case. And now you plug this in, and you break up into arithmetic progression in residue classes, mod Q. And then what you get is, and then you apply Poincare summation. And the upshot of all this will be something like this. And then Q, SQM by Q power 4 in our case, and IQ of M. So where SQM is the sum A mod Q star, B mod Q, E of A times F of B, so these are vectors, plus M dot times B dot by Q. And I is integral which can be handled. And because of the decay in M, this sum over M is actually very small. So the main issue is estimating this sum S. And what happens is this SQM is cross multiplicative, like Klosterman sums. So you can, it splits over prime powers. So you have to understand them at the level of prime powers. And the higher powers you can handle. And at the level of primes, so SPM is a product of Gauss sums and a Klosterman sum. If the number of variables were odd, it would have, the Klosterman sum would be a Sallier sum, but in our case, it will be Klosterman sum. So therefore, you get exact square root cancellation, because by well bound, this will have square root cancellation, and of course, Gauss sum besides square root P. So that is the bound that you get in the definite case. But in the, in the inhomogeneous and not definite case, in this case, in the inhomogeneous case. But in the homogeneous case, you can do better, because what happens in the homogeneous case is, if capital N equal to 0, Yeah, so all this theory goes through if it were n here. And in that case, it is cross multiplicative. But if n equal to 0, which is the case I have written, SQM, I mean, Q going to SQM is actually multiplicative. And therefore, you can write this series, Dirichlet series, in a, in terms of Dirichlet function by writing as Euler product and so on. And then using those analytic methods, you can get cancellation in the sum over Q. So that is the so-called double Klosterman refinement. And that gives you this bound. Yeah, so that gives you this bound. And Gates improved this analytic part. So up to this point, it is the same, but handling of this was done in a more careful manner, and you get some improvement. So this is the situation we are in, and now the question is, what happens if n is non-zero and the form is indefinite? So that is the thing we want to consider. So in this case, as far as I understand, this double Klosterman refinement will not work as in Heath-Brown's paper, because this is not multiplicative anymore. But in a simple situation, we have done something similar, so I'll explain that. But before that, I want to, yeah, so I forgot to tell you that the optimal choice of capital Q will be square root of the size square root P. That will make sure that the sum over M is very small. Yeah. Yeah, so now let us give some examples. So our motivation from this problem doesn't come from this point counting. It comes from a result of Selberg. From 50s, I think. So Selberg counted matrices, let's say gamma. So let's, yeah, so, okay, so let's say this is up to X. And gamma is in SL to Z. So we are counting matrices whose L2 norm is up to X. So here, if gamma is ABCD, norm gamma means S square plus B square plus C square plus D square square root. Is that visible from the last row? Okay, thank you. Okay, so what was the result of Selberg? Yeah, so then sum over n. So that is 6 times x square plus O of x power 4 by 3. And this bound has not moved since then. It is still the best known bound. But you can change the group, and there are a lot of generalizations, for example, by Duke, Rudnick, Sarnak. And there are also related works by Skin Mojesha, but that will go in a different direction. And this result has been improved recently by Blomer and Lutzko. Yeah, so now our motivation was this, that instead of taking L2 norm, you can count matrices with other norms. So what about if you take L infinity norm? So then if you take L infinity norm, the question will become the following. So replace by sup norm. So then we want to count mod A, mod B, mod C, mod D up to x, and AD minus BC equal to 1. Then can we give an asymptotic formula for this? And also you can ask the corresponding question with a smooth count. And you see this is an indefinite form, this is non-zero. So this is an example of what we have to consider. And in fact, our method will work for any forms of this form. Any, this kind of equation. And the shape of the equation is important. So if we had x square plus y square minus y square minus, xy minus zw. If we had sum of, x square plus y square minus z square minus w square equal to n, then this thing will not work, what I'm about to say. So what is our result? Before that, I should say some older results. So in fact, these questions were considered by other people. So first of all, there is a paper of Roedger from 2005, Journal of Number Theory. And what he counts is sum over gamma in SL2 of OK, where K is a number field, and height of gamma is up to X. Then you get a main term. And here the error term is, so, okay, I'll just say that in this case, saving equal to so x power 1 by 15. So over the main term, the saving is x power 1 by 15. The height means you are over a number field, so the elements have various embeddings, so you take the maximum of all the absolute values. And this is one result, and another result is comes from Gorodnik and Nevo. That's around 2010. They have this book, Annals of Mathematical Studies, Ergodic Theory of Lattice Subgroups. So they can handle any norm. And when you specialize to our situation, I should say, in this situation, if K equal to Q. So Roedger's theorem, the theorem is much more general. It works for any number field. By Q, you will get this. And Gorodnik-Nevo works in very, a lot of generality, but in this problem, the saving will be x power 1 by 16. Yeah, but of course, it's far more general. We are considering only a simple case. All right, and then our result is the following. This is joint work with Rochita Goria. This was part of a thesis last year. So the sum 1 AD minus BC equal to R, and these things to X. This is 16 by zeta 2 into sigma. So yeah, this is R. So sigma mod R by mod R X square plus pico of epsilon mod R power theta X power 3 by 2 plus epsilon. And in the smooth case, I'll just write, oh, the chalks are different. No. Okay, let me try that. Sorry? Yeah, 3 by 2. Yeah, theta. Theta is the the Ramanujan exponent. So this is smaller than 7 over 64. Okay, and if you count with smooth weight, the error term will drop to x to the 1 plus epsilon. So I will not write it down, because this is the more interesting result. W, each individual, yeah, that's a relevant point. So the first job was very good, but this one is not so good. Don't know. I'll try this one. No. Anyway. Yeah, so now I'll talk about the proof. I should also say that R cannot be too large. So this result is for mod R less than x power 1/3. And what about R equal to 0? So that can also be done, but in fact it is already done by a nice paper. And in fact, yeah, so let's write. I had Cochrane Chang. Sorry, I forgot the year, but it's in JNT. So R equal to 0 case, same problem. Then what you get is 12 by pi square x log x. Yeah, there is an extra log x always when there is a 0. So in the Heath-Brown's result also. And cx square for some explicit c plus O of x power 19 by 13 log x power 7 by 13. And in fact, it is quite easy to prove. The proof is completely elementary just by counting. Huh? Yes. Sorry, x square log x. Yeah. So what happens is if AD minus BC equal to 0, that means A by C equal to B by D. So you fix one fraction and then you multiply both numerator and denominator by some D to count D. And it boils down to an elementary counting thing. Yeah, so now I'll talk about the proof. So our techniques is to apply some Fourier analysis that transforms the sum to sum of Klosterman sum. So let's see. Proof. So let's call that SR of x 1. Okay, another thing is because of the symmetry, I can assume ABCD are all positive, because we have to multiply that by 8. That will give you the count. So BC equal to R. So the idea is to view this thing not as an equation but as a congruence, modulo one of the variables. So, okay, so the first step is you write it as, you remove one of the thing. So sum over A, sum over B, sum over C, A minus R less than or equal to BC less than AX minus R, right? So I've eliminated D, the size of D will be here. And then this minus R can be removed up to a small error. So this you write as BC congruent to minus R mod A less than BC less than AX plus small error, because I'm now removing this R. Yes, yes. So what is the congruent question? BC is congruent to R mod A. Same. Maybe minus R. Yes. Thank you. All right. And now you introduce a smooth weight. So these are from 1 to x. So this is 1. This is, let's say, x. So you want a function which is exactly 1 here. Then it should drop to 0 smoothly. So let's call this function w. Suppose this is 1 minus h, this is x plus h. So the derivative of the function will be 0 from 1 to x, and it will be at most 1 by h in these two parts. So that fact will be used. So therefore, this sum is a smooth sum. So w a by x plus big O of h times x to the 1 plus epsilon. So then I will choose h optimally later. That's not completely true. I have to put a w of bc by, sorry, there is no x. Sorry, what am I writing? There is no x. Yeah. Because w I have chosen like this, yes. And the same congruence condition. So bc congruent to minus r mod a, and here c not equal to 0. And here b and c are integers, a is positive. Okay, and next, as you can guess, we will do Poisson summation. So if you do Poisson summation in one variable, let's say b. So Poisson will give you, okay, so there is one more step, but I won't write all the details. So you can introduce coprimality. So here you can put A and C coprime, because then, if they are not, you divide by a divisor and so on. So that will give you that. And then you have AC coprime, and B is congruent to minus R inverse A, WB, and WBC by A. And here you apply Poisson on B. Yeah? Oh, sorry, RC bar, right? RC bar A. Okay, and then So you apply Poisson in B. So when you apply Poisson in B, there will be a 0th term which gives you the main term and then the other terms. So you get a main term. I mean, you have to extract a main term because there will be some more extra stuff that you have to remove, but they are not so large. Plus, you get a sum of this form. AC1, 1 by A, WA, WC. Maybe it is too small. And then sum over n not equal to 0, because n equal to 0 term is the main term. E of minus nr c bar by A and f hat n by A, where f of A comma C, f A comma C of x equals to wx w cx by A. And now you can split the sum over C into arithmetic progressions modulo A and then apply Poisson again in C. So again, Poisson in C. And that gives you main term plus sum over A, positive, WA by A square, sum over n not equal to 0, sum over m, these are over integers, Klosterman sum S, n minus m, A, yeah, there's already, sorry, that's there, and some function GA hat m by A, n by A, where GA of x comma y is wx, wy, wxy by A. Okay, and now of course you want to do apply Kuznetsov formula. The problem is this function GA hat, that's a double integral, it's a complicated thing. And then if you, on top of that, you will have to take Bessel transforms and so on, so that becomes very messy. So what we do is, this double integral, we split into parts and we extract stationary phase. Oh, there is R. Where is that? Right, in R. Yes. Yes. Yeah, so that is the messiest part of the paper, so that's why the paper is a bit long. So that is one of the main propositions. So what happens is extracting the stationary phase is not the issue is handling the error terms, because for that you have to use the Weyl bound, but it can be done. So I'll just write it down, so a lot of work. And then you get n less than or equal to m. I forgot, sorry, this is x, but these are also up to x by h after Poisson. And yeah, it's nr minus m a by a. There is x power 1 quarter. Then a by mn 3/4. Then sine minus 2 root over mnx by a minus 1 by 8. Okay, plus similar sums. So there will be total of 4 sums. Okay, and now this is somewhat manageable and you can apply Kuznetsov. But after Kuznetsov, you again get very complicated integrals. So how much time do we have? 10 minutes, okay. So then you apply Kuznetsov. And then you get some things like that. It's sum over J, so I'm only writing the discrete spectrum. Only one part of the discrete spectrum. Rho J NR, rho J M, F check, M N C. So, you know, in Kuznetsov, you are more familiar with M and C by C, so I'm replacing it by C. And of kappa J, where I have to define what FM and C is. So plus similar sums. Plus similar sums, where F, M, and C of T equal to C by Mn to the 3/4 times E power minus square root Tx Mn to the 1/4 by root over pi r power 1/4. All right, and then, I forgot to say before that once you get Kosterman sum, you can apply the Weyl bound. And then the bound you get, if you just apply the Weyl bound, will be x power 7 over 4. So let me write it here. So I'll write 3 by 2 is less than 8 by 5 is less than 5 by 3. No, 5 by 3 will be here. Which is smaller, 8 by 5 or 5 by 3? Yeah. And 7 by 4. Yeah, so the thing is, you will get 7 by 4. Sorry. What is wrong? Yeah, it's not 8 by 3, 8 by 5, sorry. Yeah, 8 by 5. Yeah, then it is less than 5. Yeah, that's what I thought. Yeah. And this is 7 by 4. Yeah, now I think everything is correct. 24, yeah. Yeah, so this is the worst bound. This is what you get if you apply Weyl bound there. And at this stage, if you apply Weyl bound, you get 5 by 3. I will tell you where you get 8 by 5. This is after Kuznetsov, no? No, this is before Kuznetsov, yeah. If you just do stationary phase, you get 5 by 3. After Kuznetsov, yeah, right. After Kuznetsov, if you apply just bounds of rho J, rho M, and Weyl law, etc., you will get 8 by 5. So there is one more round of saving after Kuznetsov, and that comes from various large sieves. And so there are two large sieves that are used. So next, we apply two large sieves. Okay, so what are they? So the first one is the local spectral large sieve. Due to Jutila. So, okay, before applying large sieve, we have to do one more round of stationary phase analysis. That's also quite complicated. And yeah, so K less than kappa J and K plus delta rho J1 by cosine hyperbolic pi kappa j summation an lambda j n. Why am I writing rho j here anyway? So this is k square plus n square. So here delta is O of 1, I think. Not. Yeah, anyway, I don't remember what size of. Anyway, so it is, the thing is delta is small. So then you have norm is square, let me write. There is a kn to the epsilon. So this is one large sieve, and another large sieve which is very interesting because it came up in the work of Desvaux and Iwaniec on the deformation theory of Phillips and Sarnak. So what happens is, after you do this Kuznetsov and then you do stationary phase, you get things like rho j n times n power I kappa j. And for that, thankfully, there was already a large sieve done by Desvaux Iwaniec, which is not very well known. So let me write it somewhere in the middle. Yeah, sorry, right, it's k delta. That's why I got confused, yes. Yeah, n is, delta is small, yeah. Yeah, so the other one is, where should I write? Right here. This is the second large sieve, which I have not seen being used in a number theory problem before, because that deformation theory is a kind of different subject. So 1 by cosine hyperbolic pi kappa j up to k, summation an rho j n n power I kappa j square then same bound basically k square plus n square nk epsilon norm a square. Yeah, so if you apply this to large sieve, there's a lot of work that I'm not talking about, this stationary phase analysis again. So then that will give you the bound 3 by 2. Yeah. And if you count with smooth weight, then the error term is just x to the 1 plus epsilon, because right after here, if you have a smooth weight like w by x, etc., this sum will just be 1. So the sum over mm is just 1. And then you apply Kuznetsov, then you directly get x. Yeah, so I think that's all.
Thank you, Satadal, for a nice talk. Are there any questions?
Could you maybe describe why this has not been used before? What's the novelty for this large sieve? Like because of that 1 over kappa j character?
No. I mean, I didn't see this before, so I was happy that it exists. It was used in this Phillips-Sarnak theory. There's very one have a paper on that. So in which they also needed to estimate such things. So yeah. No. Wait. So he another question he asked, I think.
No, I was just asking which phases and which paper.
No, this is a bit hard to look at. So this was it was a collection of articles in a conference. I don't remember. Maybe I will have to look up.
Okay, I think
it's not the famous Desvaux-Iwaniec inventionist paper. It's not there.
Is there any omega result for that error term?
Oh, I don't know.
The special case of x power 1 plus epsilon or whatever even.
Any other?
I mean, I haven't thought about it. I will get back to you.
Thanks. I was curious, do you have an effective lower bound for this singular series in this case? This sigma of R?
Yeah, I mean,
I guess you could use it, I was just wondering, you could use it to sort of produce...
no, this sigma is the sum of divisors.
Ah, okay.
Yeah, this is
I
not
see.
singular series. So.
Sorry, I thought... Okay,
Yes,
so you easily get bounds for like the effective bounds for the least solution to this equation if you're interested in...
Yeah, that's a good question. Yeah, I haven't thought about it, but that's an interesting
Seems
question.
like it would do. And I was curious about, so you said that Selberg bound is still the best known error term.
Yes.
Do you know whether there's any suspicion about whether that reflects the truth or whether...
I don't know.
Whether there's any sort of second order terms happening there?
I mean, I haven't seen anyone saying that it should reflect the truth, so I suspect that one expects better bound.
Okay.
Yeah.
Some natural help to decide whether that would be the best error term or not.
Yes.
Yeah.
Yeah, but I don't think anyone believes that this is the best error term.
Any other questions,
Yeah,
comments?
so you mentioned at one point that the shape is important, and you said you couldn't do, for example, x1 squared plus y, x2 squared minus x3 squared minus x4 squared this way. So I was wondering, is there, if you work over Gaussians, is it still not possible to do that? Like, is there something that breaks down, or?
You mean Gaussian number field, Zi?
Yeah.
Yeah, but for Zi, doing all this analysis is already quite nightmarish. Okay, but there is one more thing I want to say, that you may think that if you make a change of variable in ABCD going to a plus d by 2, etc., you will get s square plus d square minus b square plus c square. But the problem is this region will be changed to some kind of an octahedron. So inside an octahedron, you have a solution count for the solution, but not for this cube, hypercube. Yeah.
Anyone else? If not, let's thank Satadal again.